Hi everyone, how are you doing? I would like to welcome you for this webinar, and I wanted to do something a little bit different because instead of just focusing about specific feature of RavenDB, I want to start from the other side. I want to talk about how the design of applications has impacted the feature set and the way that RavenDB does things. So we're here to talk about real-time application architecture. The question here is, what exactly is that? So a real-time application is one that feels real to the user. And in many cases, it's really funny because the key here is that it feels real. It feels immediate. A user that waits for something, gets frustrated, something that happened immediately is, okay, I don't even notice that. It means that we have to be responsive. We have to be responsive. We have to process that immediately. It means that two users who are on two separate machines need to be able to collaborate together and have everything working properly, and things of this nature. So let's see exactly what it takes to build something like that. I want to remind you that I would welcome any and all questions. You can raise your hands. You can ask them in the chat as well. And let's see. Okay. So close only counts in horseshoes and hand grenades and users' perceptions. So this is something of a key. If you are bound to, oh, I have to do and process everything inline immediately, then you put yourself with a huge limit on the kind of functionality behavior that you have to do. But it doesn't have to be this way. The only thing that you need to do is to appear fast. And there is a very important distinction here. So what is fast? Fast is anything that the user doesn't have to think about. So if you're showing a spinning wheel for the user, that's not fast. If something happens immediately and it just works, even if behind the scene there is still processes going on, the user doesn't care, but the user experience and the behavior that you generate is really, really important. Now, eventually you have to do the work, but the fact that you don't have to do the work inline has a huge impact on your system. By the way, even if you have to do expensive work, there is a lot of stuff that you can do to optimize things if you know that you handle them in batches. For example, I see that my workload is very high. I'm going to spin up new instances. But because I don't have a user waiting for me, I don't need to worry that, oh, I can't spin a new instance to handle new cloud machine instance just because a user is waiting for me. There is not enough time for that. But if you control it in the backend, that's absolutely something that you can do. Probably something you wouldn't have to do, however. So let's talk about this. The first thing that we have to understand is what is the latency target for the user. And in general, we want to aim to under 150 milliseconds. And the magic number, by the way, is 200 milliseconds, which is the perception threshold for human. But there have been many, many studies that have shown that users can feel it even if the latency of the page is just an extra 100 milliseconds. And for Amazon, this meant that every 100 milliseconds meant 1% of the users just left. And for Google, I think 200 milliseconds in additional latency for the page meant that about 20% of the people would leave. Now, think what it means in terms of the impact it has on the business, on your applications. If you can save even a few milliseconds in the response time, that can result in a huge conversion rates, in better retention times, all of those metrics that people care about. But the fourth thing that we need to understand is we need to set and maintain some sort of a budget. And this turned out to be quite hard. The moment that I have to interact with anything external, I cannot meet that limitation. Just the ping time to some external servers is greater than 150 milliseconds. So I can make it work. So you have to understand that when I designed RavenDB, and we're talking about 12 years now, more or less, I did not do so in vacuum. At the time, I was mostly dealing with performance consulting for a whole bunch of companies, and I was focused a lot of time at the database layer, well, obviously, but in many cases, I would come in and says, hey, you don't have to do things like that. Let's change the way that we're doing things in order to make things easy. And when I started building RavenDB, a lot of things went directly into that. So part of the core design of RavenDB is that we prefer and explicitly optimize response times over almost everything else. So let's talk about what this means. For example, you send a request to RavenDB. RavenDB will prioritize that internally in over a background work, to optimize that over a whole bunch of other things that that we can do. Running ongoing tasks, backups, replication to other things. User requests and API calls are the primary thing that we're here to serve. That also means, for example, with indexes. RavenDB doesn't handle indexes inline. Now, in this case, RavenDB has two different things that it needs to balance. On the one hand, we have the desire for very low latency. On the other side, I'm not willing to give up the transaction guarantees. So somehow we have to meet them in the middle. So RavenDB is a very fast database that is also able to give you a transaction guarantees. And we do a whole bunch of work behind the scenes to make this happen. The most obvious example here is that indexes in RavenDB are running in the background. Why does it matter? It matters because I can complete the transaction and return the results to you before the indexes run. Conversely, it means that when you query the index, you don't have to wait for the other transaction to complete. You don't have read or write lock here. You're going to get the details that we have as is. Now, typically, we present that as a downside. Or when we're using RavenDB in this format, that means that we have stale queries. And you know what? We can actually see it here. This is the public instance of RavenDB. It's available for everyone. The RealTime. Now I'm going to go here and create some sample data. Yes, and now what I've done here, I've paused the data, paused indexing. Because indexes are actually running as a background process, I can do that. And that actually has some important impacts in some cases. But the reason I'm doing that is because I want to be able to see, it says, oh, you can see that there are 5 orders for companies 85. Let's go and see what this means when I'm adding a new order for company 9. So we have 5 orders here. Now, what we're doing right now is simulating slow indexes. But notice that the time that it took me to generate the query was minuscule. Why is that? This is here because I don't have to wait for this. I can just make it run, and I'm done. Now, if I'm going to ask, what about company 9? Here I have just 17. This is wrong. Let's fix this. Let it run, and let's see what's going on. Now we have 18. But this query is still right. So what's the point? Why am I showing you that RavenDB can return bad results? Well, the answer is not bad. The answer is still. And this has a huge impact on the design of your system. Because for the most part, queries don't generally need to wait for indexes, especially indexes from different or operations that happen from different users. And given that the indexing latency of RavenDB is in milliseconds, you generally don't have to think about that. But it also means that the query latency and our ability to manage the state is much higher. You don't have to wait for things. You could. There is a feature that you can element says, oh, I want to wait for the index to complete, either on save or on query time. But you don't have to, which means that you have the ability to optimize your system far better. There are other things that RavenDB does quite nicely. For example, we have automatic caching built in, all sorts of stuff like that. But that's a lot of that ends up being, okay, let's think about what we need for my application and then make it work. RavenDB also does a lot of batching behind the scenes. If you have two concurrent writes going on at once, RavenDB will only go to the disk once for both of them. That significantly improves overall performance. When we need to index, one of the advantages that we have with deferring the index work, even if it's just by a few milliseconds, is that we're able to gather a bunch of updates all at once. And that gives us far better alternative for the overall performance of the system. Because, oh, now I can do things in a bulk fashion. Okay, moving on. So I mentioned before that save changes doesn't wait for indexes to run by default. You can say I wanted to wait for a specific index, etc. Another thing is that important is that MapReduce indexes. And this is a MapReduce index, orders by company. It does not compute during the query time. This happens behind the scenes. So on query times, what do we have left? Just fetch the data. For that matter, RavenDB does not allow you to do computation at query time at all. You can do computation on the results, but to find what the results are, that's not possible. And that is by design. That is a very explicit design choice that we made. And you can see why here. We have an index, and I found that to most people, talking about the phone book is the easiest way to explain that. If you're too young to have used a phone book, go to the library. It's a building with books and research that. Do not use Google. That's offensive. But the basic scenario goes like this. A phone book has a list of people sorted by last name and then first name. Today, I would assume this is called a data breach. But the basic idea is that if I want to query for the phone book of a person using their last name and first name, it's triggered to do so. O log n to complete the query. What happens if I want to find all of the people whose name is George, where George is the first name? Well, as you can imagine, that's going to be quite expensive. I have to scan through the entire phone book because I cannot use the sort order of the names in the book. Same thing if I want to find, let's say that I had the, I don't know, date of birth or address in the phone book. I want to find everyone who lives in, I don't know, Yellow Brick Road. If it's not in the index, that requires a scan. And a lot of the time, computations during the indexing, the computation during query time is horrendously expensive. Let's look at something like this. We have form employees. And for some reason, it does not respond. Let's try it again. Okay, form employees. And you can see that we have birth date. So if I want to do something like this, it would be very helpful if I could spell. I assume that I can spell now. What's birthday? Yeah, it would help if I could actually remember. Okay, so here are the results. Now, another way of specifying that is to say, you know what? This is a query that requires to compute. This is a bad query. We have to run this expression on every single result in the system. Now, I can do the exact same thing if I do this. And the reason this matters, this can be implemented by scanning the index. Go to the birth tier and go up. And that's it. Cheap, easy, all again, and then scan off the results that we have. Now, I'm using terms such as all again and ON and stuff like that, and those are typically used to discuss the algorithmic complexity of our algorithms, the computational complexity of our algorithms. Now, I'm using them because they translate directly into the runtime of the query. And given that I spent so much time as a performance consultant on databases, the design of RavenDB was explicitly meant to minimize the options of you being able to create a bad query. Now, let's look at this. I want to do an aggregation. And you can see here that aggregation is done to MapReduce. And MapReduce doesn't happen at query time. Let's go and look here. Orders by company. This is for 830 orders. I'm going to go and try to do better than that. So what I'm doing here, I'm modifying the data, and for each one of the orders that I have, I'm going to force it to execute additional, to create another 100 orders. Let's look at how this looks like from the backend. I should probably mention this is a really, really crappy machine. So you can see 2 cores and 2 gigabytes of RAM, and it is still able to process 15, 32, 36, 100 writes per second. And we effectively saturate the machine, which is good because while we are doing that, I want to be able to go here and run the query. And notice that it completes in 3 milliseconds. Now, this is a stale result, but that's the key point. Okay, it's done. So again, run this again. The results are in stale. It took me 0 milliseconds to do that. Now let's run this again. Now we are going to move from 90,000 items to 8 million or something. And while this is happening, I get to keep running this. But I notice that in some cases this is still, in some cases this is not, because we're able to keep up with the rates of writes. Mostly because we're able to do those sort of optimizations. So the whole idea here is that we want to move as much as possible the cost of computation of expensive stuff into the background, into doing things in indexes at indexing time where I have a lot of chance to optimize things. On the other hand, when I'm querying that, full speed ahead. There is a user that is waiting for me here, and I absolutely want them to be as fast as possible. Now, there is a story that I really like by Robert Heinlein, The Tale of a Man Who Was Too Lazy to Fail. And I strongly recommend that. And the whole idea here is that you want to be lazy as possible. You want to do as little as possible, but at the same time, that actually requires prior thinking. That requires you to manage quite a lot of details. So one of the primary issue that adds to latency, that adds to the slowness of the system, is this: network latency. Going to a remote server is expensive. Let's see here. This is still running. No, it's done. I think it's done. Okay, this is strange. 1 second. No, it's still running. Let's abort that because I want to show you something very interesting. So now I'm going to run this. You can see that the query time here is 2 milliseconds. Let's make sure that we're not using a cache. And here we go. This is important. Notice here. So server side, this cost me 0 milliseconds. This is the query. Notice how much it cost me. Now, what did I actually get here? I got here 232 milliseconds just for network latency, because the cost of the query on the services is nil. Now, let's say that I want to show this in a grid. I need the username. So now I have to go and say, hey, give me companies 34. That's expensive. That's mean paying another 200 milliseconds in latency. Or I can do this. 1 second. Let's clear this again. Now, no cache. And now notice what is the timing now. This is actually interesting. It doubled the time. It should not have done that. Let's see what happens if we do this. That's actually quite interesting. I would not expect that. Let me try this again. So apparently the latency is big enough that we're actually seeing the difference in the size of the content. But we'll still have just a single request to the server, and you can see all of those things here. Now, at the same time, I can say, you know what? Let's go here. Count c.count, total c.total. Load c.company. Here are the results. And hopefully now, this should be much, much faster. Let's run this again. So it does the parsing. Yeah, so now we're seeing more reasonable time frame. But let's look at the actual API that we use to run this. And you can see that in terms of the API that we use, sorry, not this, query. I just need to tell it to you, this, include the related data. So now when I'm calling this doesn't go to the server. It doesn't go to the server because I already included the data. Single shot. Lazy is similar. Lazy is similar because it allows me to issue multiple independent queries as a single request to the database. Now, I'm spending a lot of time of this, I know, but this is important. This is important because this is one of the cheapest way you can optimize your system by just reducing the queries. And you know what? I recently had seen someone do something like this. What they wanted to do was they wanted the paging. So they're saying, okay, give me all of the four-star results, but then give me the count, the total count without the paging. Now, this is a remote call, and this is a remote call. That's expensive. But let's see here. I'm getting 10 items here. But let's see what RavenDB sends over the wire. I have total results and I have capped max results. Now, the reason that I have capped max result is obviously because I said 10. But I can show you right here. I'm already sending you all of those details over the wire. And now you can do this. Not here, here. And now we're done. One request to the server. And it matters. It matters a lot. Now, so far we just basically talked about performance, but there are also other things that we want to handle. One of the things that makes for a real-time application is the fact that we have to deal with user interactions and interactivity. And consider the case that I have an application that is running on multiple nodes. And I need to somehow interact between different users. Maybe, and the classic example is two users who are editing the same invoice and want to show them the changes, stuff like that. So the way that we can handle that is through a dedicated API dedicated API in RavenDB, which is called the Changes API. Let's see a demo. And RealTime. And what you can see here, this is about as stupid as it sounds. I mean, this is the code. Start changes, subscribe to changes on all documents, and react somehow to those changes. So let's see what happened on Thingy. No, on Thingy. Let's see what happened when I'm running this. Now I'm going to go here and delete this guy. And here you can see it's been deleted. For that matter, let's run them both together. You can see the response times. Now, the interesting from our perspective is what this means. What this means is that we can go to RavenDB and ask it questions, interesting questions about what are you doing, how are you doing things, and then we can say, hey, let me know when something happened. Instead of me asking the question, I'm reversing things that, hey, you're responsible for letting me know when something happened. And the way that it works is fairly simple. In this case, I'm saying for all documents, but I can say for a particular document. And now I can react to this in my code. So I have here a Blazor application. It's not a very good one, I will admit. And what you can see is that I have a hub, and the client code can register. And when you register, you open the changes, you register for a particular document. And when this happens, you send a notification back to the client. So notice what we have here. We have on the one hand, we have the client, we have your application, then we have RavenDB. RavenDB raise a notification, send it to application, that send it to the client. And that makes sense. And as you can see, there is almost no code here at all. Here you have the other way around. Oh, I don't want it. I'm leaving the page, stuff like that. I'm going to just move away. I'm done. And this is a very powerful system. Think about what it means. It means that you don't really need to manage a lot of stuff yourself. Oh, I just need to know what are the things, what are documents the user is looking at right now, which is, honestly, it's very easy to know that. And then I can just move on and manage that easily, cheaply, and with no fuss. But let's see. Okay, so one of the key aspects here is the notion of user interactions in interactivity. So the user does something in one location, it gets sent to the server. We do minimal amount of processing and throw it into Raven. At the other side, we have a changes API that watches over that and can react and send notification to the user, to another user, not to the same user. So we have two users that may be working on the same thing. One of them changes, the other one starts blinking as well. And that's a very powerful thing to have because, oh, I don't need to think about it. Things just work. As a user, I don't need to think about it. This is also really good if you want to implement more dynamic features. If you ever seen multiple edits in Google Docs, something like that, this isn't actually the other user typing live. This is the server sending you the modification that they made maybe 5 seconds ago, or something like that, and then you're seeing this show up at the same rate that it was entered. So from a perception point of view, this feels much more responsive and alive. Now, I want to mention that there is a big difference between the changes API and subscriptions. A subscription is a reliable process. It runs and can restart. It doesn't lose data, guarantee delivery, those sort of things. Changes is a lot more transient, but it's also a lot more lightweight. It means that you can have quite a lot of them, and internally they are piggybacking on the same set of connection or much of other stuff like that. So they are quite cheap. The reason this matters is that a lot of really good architectures can be said, can be designed. I don't want to do things right now. I want to do it at some other point. So the idea here is that we accept something from the user. We do the minimum amount of validation and processing that we have to do right now. Maybe even to the point that we're just showing the data to the user without even going through the motions internally. Only the user who modify the data will see the actual modification, because this is now being bundled and saved to the database. Some other process, likely a subscription or an event of some kind, is going to pick up that command and operation and start running that. Consider the case that I want to pay an invoice. So the way that it works is, okay, I'm going to give my credit card details and hit pay. And what will probably happen is that I'm going to say something like, hey, let's validate this is a valid credit card, cheap in memory operation. And then I'm going to throw that payment request into Raven. And a subscription will pick it up and try to do the actual charges. Now, if everything is successful, then we're good. And what I'm actually going to do immediately is mark that invoice as in green with the status of payment in progress or something like that. If there is a problem, I'm going to set the status to a problem. And then using the Changes API, I'm going to pop up some message for the user. If this is, and this is the standard case, this is perfectly fine, then the user is going to just say, oh, the system reacted instantly. Now, I want to spend a few seconds talking about the outbox pattern. In the outbox pattern, we have an issue. This issue is that we want to do something like a invoice.status. So we have two parts of this. The first part is when we need to send to the queue charge this invoice. The second part is when we want to modify the status. Now I can do this, but now I have a problem. What happens if I have a failure here? I already saved the document. It's already saying payment in progress. But I'm never going to charge that because I failed to put the item in the queue. On the other hand, what happens if I'm doing this? And now I have a failure here. I start charging the invoice, but haven't set the value. Now, in this case, this is a relatively simple operation. But you can imagine that as the complexity grows, this becomes a lot harder. This is especially the case if I have to deal with a situation where I may want to send multiple documents, stuff like that. Instead of doing like this, I can do this. Now, all of this as a single transaction is going to be persistent. Another process is going to start running once that transaction is committed. This may actually dispatch the command directly. It may send it to another queue, etc. But the whole idea is that I'm looking at everything in terms of a single transaction boundary that is safe for me to operate in. All of those modifications are handled properly. The other thing that we have to consider is the overall architecture. And the overall architecture of a real-time application is that I want to do as little as possible as a result of user interaction. Throw data with minimal processing, fetch data that has already been digested for me, and then push all of the other things that I want to do into the background for a whole lot of reasons, for scaling issues, for being able to do batch operations, but for the most part, this is the key here, because the user interaction model is so different and generally so much better. And with that, I would be very happy to answer any questions that you have. We actually have some questions that were sent in advance, so I'm going to answer them right now. We have Simon, who is asking, can I integrate changes with SignalR, gRPC, and something like that? How do I handle such a system? So I think that this thing is pretty much how you handle that. You associate a changes operation with a relevant caller, and then you just invoke it properly. Admittedly, this is not a good, this is not an ideal system for that, but it works and it shows the way to go about this. How would you scale such a system? That depends on exactly what you're trying to do. I want to point you out, one second, if I would be able to properly look things. So you can see here, this is a white paper that we recently issued, and it talks about performance numbers and things like that. And this is RavenDB, and this is RavenDB handling here upward of 15,000 queries per second at pretty good numbers. Now, if you want to do this slightly more interesting, you can see what happens when we have this query. And this is a query that allows us to do a prefix on a prefix query on the document ID. And now I can see that RavenDB is processing 50,000 queries at 99.98 percentile. So 2 requests out of every 10,000 took longer than 200 milliseconds. For the most part, scaling those sort of systems is easy, even if you're talking about ridiculous number of operations. If you want to go to 30,000 queries per second, stuff like that, that means, and just to give you some idea, 30,000 queries per second times, this is in 1 hour, 1 day. So that's in billions. That's a huge amount of numbers. If you look at the top rank website, not the top 10, but the top 50, they're seeing on good days 500,000 requests per second on a sustained basis. They have peaks of more, but RavenDB is able to process that without too much of a hassle. We have a question from Owelas. I hope I'm pronouncing the name properly. And the question here is, are the capabilities shown here are tied to a specific license? And the answer is no. you can run it on anything, on any of the feature sets, including the community. We have Asrit J, I think that's the name. Is there a chance to perform NLP on the database? NLP stands for, I assume, natural language programming or processing. And the answer is yes. The answer is absolutely yes. And the way to handle that is RavenDB 5.1 added support for integration with NuGet. And let's see if I have this available here. Yeah. So the idea here is that you can define indexes that are going to use NuGet or whatever you want. Where is NuGet? Here we go. So you can use NuGet as the source. You can run additional code here, and you can apply it during indexing time. What this means in effect is that you can do whatever you want. If you want to do some processing using whatever algorithms, machine learning model, whatever, you can do that during indexing, and then this expose outside. Astrid also asked about support for full text search. I'm pretty sure that we have a webinar on that already, and you can RavenDB webinar. Let's see that. I'm pretty sure we had something here recently because I remember talking about this. Let's go. Yeah, here we go. So this thing is, I think I would answer your question. You can watch that. If you have any additional questions, please let me know. Ram wants to see database scaling for business growth needs. Ram, I don't think you're here right now, but please talk to me or send us an email or something. What exactly you want? And again, scaling RavenDB is relatively easy. And you can see here that this, in this case, by the way, you can see that this is RavenDB running on fairly large instance. Let's say, I think those are the numbers in terms of cluster sizes. But notice that this is RavenDB running on three servers with 2 cores of ARM instances. And this match the performance of the system to the 95th percentiles at 10,000 requests per second. Again, really very, very high. Simon Birrer is asking observability and monitoring. I had another webinar on this and about operational behavior. Let's see, it's either here or in the one. Oh, yes, this is also a good one about indexing. And this is if you want to learn more about we want to learn more about machine learning and NLP, that would be a good thing. For operations, this is the thing that you want to go on. I do want to talk about an upcoming feature that we have, and this is the 6.0 version, where we're intending to implement server-side sharding, among a few other interesting features. We actually have the design of that already public. So you can go to here, and we have quite a lot written on exactly how this is going to work, the motivation and stuff like that. Generally, I'm going to assume that for most users, this isn't relevant because we're already plenty fast enough. And this is it for today, unless you have any further questions. In the meantime, as a reminder, we also offer live demo. If you want to talk to us in private settings, want to see how RavenDB is run, can be used in your environment. And also, apparently, you need to update Java. The answer is later, because they don't have never. And that's it, guys. Thank you very much, and goodbye.